Hi guys, today I'm going to be working through the 85s, which is the first sig fig homework sheet that we have for you. I'm going to go through a couple examples in each section and hopefully go slow enough that you can make some sense of it and help you out with identifying how many sig figs are in a number, scientific notation, and then doing some multiplication or division, as well as some adding and subtracting. So, I'm on the front side of the 85s. Let's look at problem number 3. Okay? So in this problem, we're just trying to identify how many sig figs do we have. So, if in number 3, you notice that we have 5.34 times 10 to the 15th power. Anything with scientific notation, we completely ignore the times 10 piece of that number when counting sig figs. In other words, all I need to look at is the 5.34 piece in front. Okay? So any value that is a non-zero, meaning any number 1 through 9, is significant. In other words, 5.34 times 10 to the negative 15 has 3 sig figs. Okay? In the next one, number 4, 1.54, okay, or 0.154, I'm sorry. The 0 in front, if you have zeros to the left of your first non-zero, they never, ever count. This is rule number 5. Okay? So that 0 is not significant. 0.154, those 3 are. This is 3. In number 5, we have 197.042. All of those numbers that are non-zeros count. And that 0 in the middle is trapped by non-zeros on either side. Zeros that are trapped or captured do count. So this is a total of 6. Number 6, I have 700.4. Again, those zeros are trapped. They count. So I have 4 sig figs. Number 7, another trapped 0. That 0 is between a 1 and a 5. Therefore, it also is significant. We have 4. In number 8, a little different rule here. Now I have zeros to the right of my last non-zero. So my last non-zero is that 6. Okay? And all of those zeros are to the right of it. Now, if there is not a decimal in my problem, those zeros are not significant. In this case, we only have 1 sig fig. In number 9, I have 5.000 times 10 to the 12. It's scientific notation, so I ignore the times 10 piece of it, and I count my sig figs out in front. These zeros are to the right of my last non-zero, my 5. There is a decimal in my problem, so these do count. This is 4 sig figs in number 9. Okay? So that's pretty much the pattern. Zeros that come before your first number never count. Zeros that are trapped are significant. And zeros to the right of your last non-zero will be significant if there's a decimal, and they will not be significant if there isn't. I'm going to switch gears and jump to the lower portion on scientific notation and show some of these. When you turn a number into scientific notation, essentially we are moving the decimal place. Okay? In the first example, we have 0.0025, and I want to change this into scientific notation. So I'm going to take my decimal, and I'm going to go 1, 2, 3, and place it right behind my first non-zero. When you do scientific notation, the decimal always, 100% of the time, ends up right behind the first non-zero. So I move it 3 places so I can get it behind the 2. I rewrite my number. 2.5, and then I write times 10, raised up to some power. The power that I use on my 10 is dependent upon how far I moved my decimal. So in this problem, we moved it 1, 2, 3 places. My exponent, or my power, should be a 3. And now the question comes in, well, should that be a positive 3, or should that be a negative 3? If the original number is less than 1, your power should be negative. If the original number is bigger than 1, the exponent should be positive. Let's try the next one. So in 19, I need to move my decimal until I get it right behind my first number. So I'm going to go 1, 2. and put it right behind the 1. I rewrite it. I include times 10. And then I put an exponent equal to how far I moved my decimal. In this case, we moved it 2 places. And my original number was bigger than 1, so it should be a positive 2. Number 20, we're going to move the decimal again. We got to move it until it ends up right behind that first number. So I'm going to go 1, 2, 3, 4 places over, and I'm going to rewrite my number. Now, it hasn't come up in the first 2 problems, but in this problem we have a 0 behind that 2. The question is that a significant digit or is that insignificant? Well, zeros to the right of your last non-zero do count if there's a decimal in the original number, and there is. So when we turn something into scientific notation, we absolutely need to include all of the significant numbers that were there before. So I moved this 4 places. I'm going to rewrite it. That 0 behind my 2 is significant. I need to include it. So I have 2.0 times 10 raised up to the power of how far I moved it, in this case 4 spaces. And then I can decide whether this is positive or negative. Because my original number was less than 1, it's a negative exponent. I'm going to go a little quicker on these next ones. Please follow along. This next one, I move 1, 2, 3 places. I rewrite my number, 9.8765 times 10, raised up to the power of how far I moved it, in this case 1, 2, 3 places. And my original value is bigger than 1, so I have a positive exponent. The next one, I go 1, 2 places to move my decimal behind my first number, rewrite it, 2.5049 times 10, raised up to the power of how far I moved, 2, and this is negative because my original value is less than 1. The next one, I'm going to move 1, 2, 3, 4, 5 places, 1.250 times 10 to the 5, and my original number is less than 1, so this is negative. In this problem, I have to move it 1, 2, 3 places to get behind my first number. I write 1.0000 because all of those zeros are significant. I need to keep them in my scientific notation. Times 10 to the 1, 2, 3 power, because that's how far I moved it. And my number was originally bigger than 1. It's a positive exponent. In the next one, I write 1, 2, 3 places. So I write 1.234,000. Again, because those all are significant. Times 10 to the 3rd power, and it's a positive exponent. Last but not least, I have 1, 2, 3, 4, 5, 6 places I have to move my decimal. I write 1.000001 because those are all significant, times 10, raised up to the 1, 2, 3, 4, 5, 6 power, and it's positive because my original number is bigger than 1. Let's do some math. Okay, the top 5 on the back side of this sheet are related to multiplication and division. Multiplication and division rules for sig figs say that we can only have the least number of sig figs in our answer as there was in the problem. So if we look at 30, this first number has 4 sig figs. The second number has 2 sig figs. Therefore, my answer can only have 2 sig figs. Now, if you're checking these boxes, okay, all 5 of these multiplication and division boxes are related to the number of sig figs in the data. So, you can do that. I plug this in, and my calculator is going to tell me that I have 92.44. But when I report my answer, I can only have sig figs equal to the least number that was in my problem, which is 2. So I have to round my calculator answer to 2 sig figs. So if I look at rounding this to 2 sig figs, I'm going to end up with just 92. And then I should label my work grams squared. In the next one, we have 80 multiplied by 0.84. This 80 does not have a decimal in it, so that 0 is not significant. In other words, that's 1 sig fig. The 0.84, that first 0 doesn't count because any 0 that comes before my first non-zero is not significant, so I have 2 sig figs. My answer can only have the same number of sig figs as the least number in my problem. So if I punch this in, my calculator is going to say that it's 67.2. But in reality, I can only show 1 significant figure in my answer, so I have to round. If I want to round this value to 1 sig fig, I look at the second place. At that 7, it's bigger than 5, so I have to round up. And I end up with 70 without a decimal meters squared. Okay? It's important to not include that decimal because if the decimal is there, you're really saying that that 0 is significant. And you're saying you have 2 sig figs, which we can only report 1 in this problem. In 32, we have a division problem, same rules as multiplication. So if I punch in, or I'm sorry, let's go through the sig figs, my bad. So if we have 34.981, that's 5 sig figs. If we have 2.0, that's 2 sig figs. Our answer can only have 2 sig figs. So I plug this into my calculator. My calculator tells me that I have 17.4905. Again, we can't give all those digits in our final answer. We can only give up to 2 sig figs. So our final answer, if we round to the second place, we would look at that 4. That 4 is less than 5, so we would round off, giving my final answer of 17. We have to include our units. When we divide units, we simply use a division symbol in our label. So this is joules per degree C. Okay. So that's the general process for multiplication. The next ones have some scientific notation, which makes it maybe a little more difficult to enter, but the process is still the same. Let's look at 33. 1.00 times 10 to the 23rd has 3 sig figs. And again, when you look at scientific notation, we completely ignore the times 10 piece of that when counting sig figs. Below that, we have 2.3456 times 10 to the 14th. That's 5 sig figs. So our answer can only have 3. We plug this into our calculator, and I would encourage you to use parentheses for any scientific notation number. It's safer in your calculator to make sure that your calculator doesn't accidentally do the order of operations incorrectly. So I plug this in, and my calculator is going to say 426,330,150.1. Some massively huge number. We can report this one of 2 ways. We can report it with 3 sig figs as a normal number. The way we would do that is we'd round to the 3rd place. So we look at the 4th digit, which is a 3 less than 5. We should round off. So my final answer could be written as 426,000,000 we would label it grams per milliliter, and that would be perfectly fine. But you could also report this as a scientific notation value. It might be a little easier even. So if we do that, we would have to move our decimal place, and I would go 1, 2, 3, 4, 5, 6, 7, 8 places over, and I could rewrite this as 4.26 times 10 to the 8, because that's how far I moved my decimal. Okay. Both of those values show only 3 sig figs, which is what our answer requires when we do this problem. I'm going to move on to addition and subtraction for the final set of rules. And if we look at addition and subtraction, it's a different rule set that we have to follow. If you look at the next box over up top, we had to put an X in a box for which rules apply. The second box says that the calculation deals with how precise the data is. This is the rules we need for addition and subtraction. So let's look at that first one. We can plug that into our calculator. 34.49 plus 102. The calculator is going to tell us 136.49. Now, if we go back to the original problem, our answer can only be as precise as the pieces we used, or the least precise piece of information in the problem. So the first number here goes to the hundredths place. The second number here goes to the ones place. Our answer can only go to the ones place. So if we go back to our calculator answer, we would have to round that thing to the ones place. So I look at the value past that, the 4. That's less than 5. It's going to get rounded off. So I end up with 136 grams as my final answer. In the next one, we look at the precision again. 60 with a decimal point means that that 0 is significant. So the first value really goes to the ones place. The second value there goes all the way down to the thousandths place. The least precise of those two is the ones place. So I'm going to take 60 minus 5.300, and my calculator tells me 54.7. But I can't go to the tenths place in my answer because the least precise piece of data went to the ones place. I have to round to the ones. I look at the place after, or past that, which is a 7. That's bigger than 5. I need to round this up. So I turn this answer into 55 grams. I'll do one more. Let's look at 37. In the first example, this answer, or this piece of data goes all the way down to the thousandths place. My second piece of data goes down to the tenths place. My answer has to end or stop at the tenths place. So I put in 0.012 plus 1.5. The calculator tells me I have 1.512. But I can't report my answer like that. I have to stop at my least precise piece of information. So I have to stop at the tenths place. I look past the tenths place at the value after it. That's a 1. That's less than 5. I'm going to round off. And my final answer ends up being 1.5 grams. I hope this was helpful, and if you have any further questions, don't be shy. Please come find Mr. Schreiber or myself, and we'd be happy to help you.